Okay, we're going to do number 5 in the packet. Now, the schedule is a little fouled up because tomorrow is the day they're giving the test to the sophomores, and so I have to help with that. But that means A Day doesn't get, there's no A Day tomorrow. Like Friday's another B Day. And so to try and keep all my classes in somewhat synchronization, and also because this is challenging, I don't want you doing any homework. We're going to work on 1 or 2 problems in class today. You don't need to go do anything after that. Just come back to class on Friday, we'll start working on it again. I want to get to the point where I feel confident we have done enough together that when you start working on your own, the frustration level will be manageable. So, everybody understand? Everybody good? Okay, cool. So we're going to start with number 5. I've already made a video for 1 and 2. So taking advantage of the fact that the concepts presented in 5 are pretty much identical to the concepts in 1. So it gives me a chance to have more than 1 video posted to give you extra help. So 5 is asking us to calculate the value of an integral. If you were allowed to use your calculator, super easy. Just pick it up, type it in, press enter. However, we are preparing now for the 80% of the AP test where you are not allowed to use a calculator. So the goal today is to learn how to calculate that integral without a calculator. And the method we're going to use is, of course, the most tested idea on the entire AP test, which is the fundamental theorem. So here's a version of the fundamental theorem. And the fundamental theorem says that if you are integrating some formula, now in this particular example, the formula has been named f prime. That's not important. Like, really, say it again. It's not important that that formula is called f prime. What is important is how that formula I circled in green relates to the formula I am now circling in yellow. That's what's important. So I could have written the fundamental theorem like this: the integral from a to b of, let's see, small f dx is exactly the same thing as this other formula called capital F and that's just a different version of the fundamental theorem. Because it doesn't matter how you name the formulas, what is important is how the formulas relate to each other. So we'll go to Sam here for a second. So in the fundamental theorem version here, Sam, we have a formula circled in green, we have a formula circled in yellow. So for the version up here, how is the green formula related to the yellow formula? In just very simple terms. And we've been studying it for quite a while. How does this formula we're calling f prime relate to this formula we call f?
Aren't we like finding a position or like a specific value of f?
2 points for that. You're remembering a version of the fundamental theorem that would look like this. If we integrate the velocity over some time period, that's no different than comparing 2 different positions. So that's another version of the fundamental theorem. So we'll go to Will. So Will, fundamentally, in all these examples, the green formulas are related to the corresponding yellow formulas in an extremely specific way. So up here again, Will, how is this formula I circled in green related to the formula I circled in yellow?
The formula in green is the change in the formula in yellow.
There we go. Let's write that down. So 3 points for Will. What he said was, if I take the yellow formula, f of x, and I find the derivative of that formula or the rate of change of that formula, I create a brand new formula called f prime. That's how they relate. The green formula here is the derivative or rate of change of the yellow formula here. No different on every line on the board. This small f has to be the rate of change or derivative of this capital F over here. So I could do the same thing I could write on the board. The derivative of capital F must be small f for this version of the fundamental theorem to be true. The derivative of velocity, the derivative of the position is the velocity. The derivative of small f is f prime. So let's write that one down just to be complete. So the derivative of the position, that is the velocity. That's how the two formulas have to relate to each other. Questions about anything, please?
Just on the, for the blue, like on the second line, the blue line, for the yellow formula, should the second one be FA and not B?
5 points for Ellie, nicely done. Cool. Anybody else? Herb. Okay, so that's where we start. So we look up here and we notice the fundamental theorem tells us the following. The theorem says that if you're trying to find the integral of this green formula, one way to do that is to do what we have been doing. You use your calculator and you perform this multiplication between these two green things 1,000,000 times. And that will calculate the integral. You add them all up. But the fundamental theorem says there's another way. If you could find this other formula called f, or whatever we want to call it. In fact, let's do this. We'll get Cecily to help me. So once again, Cecily, how is this green formula here? Sorry. How is this green formula right here related to this yellow formula here? Can't get the yellow to work. Cecily, how is the green related to the yellow?
The green is the derivative of the yellow.
Perfect. So now you can turn it around and you can say this. The yellow is the antiderivative of the green. So the green is the derivative of the yellow. The yellow is the antiderivative of the green. 2 points for Cecily. So the fundamental theorem says if you don't really have you don't have a calculator, you can't calculate the integral of this green. The fundamental theorem provides another way. It says we can go find the antiderivative of the green formula, and then all we have to do is plug into that antiderivative formula 2 values. So we can do 2 computations right here, 2 calculations. And that's equivalent to 1,000,000 calculations over here. That's our strategy. Questions about anything? Please.
What's the difference between antiderivative and integral?
Gotcha. So integral means take whatever this formula is right here, like whatever is given, perform that calculation over and over again for 1,000,000 different x's and add them all together. That's integration. Anti-differentiation is much, much simpler, really. Anti-differentiation means this. 3 points for Delina. If I have a formula called f, we'll do a really simple example. And this formula happens to be something like x cubed. We'll go to Emmeline. If I apply the ddx operator to both halves of the equation, what would I write for the very next line, Emmeline?
df of x over dx equals 3x squared.
Very good. And I could also say, using the chain rule, this could be written like so. F prime of x dx dx. And then this would be 3x squared, 2 points for Emmeline. That's finding a derivative. Pretty good. now we can do this. We can apply the antiderivative operator. So notice the derivative operator was d over dx applied to f. Here's how we apply the antiderivative operator. It's the same symbol because they are related. So I apply this operator to f prime. And notice how I had to apply d over dx. Here I apply this dx. So it's a part of the operator in a similar fashion. I do the same thing to the other side. Questions so far? Cool. Now you look at your sheet and you notice there is no constant rule listed. My thought was you've used the constant rule enough with derivatives that you probably don't need to have a rule stated. So just like with derivatives, we can pull the multiplying constant out. So right here, we already just said it. The antiderivative of f prime is simply f. So the antiderivative of f prime of x is simply f. On the other side, we can pull out the 3. Now we have the antiderivative of x to the third. I'm sorry, x squared. We'll go to Matthew here. So Matthew looks on his brand new blue sheet. He looks at the top left corner. He says a rule that says the antiderivative of x to any exponent. So what is this the same as according to that rule sheet, Matthew? So the rule sheet says the antiderivative of x to the n dx is the same thing as x to the n plus 1 divided by n plus 1 plus a constant. So we're trying to make sure that this is an exact match for this. So what's n in our case, Matthew?
Is it 2?
So the n is 2. That means we don't have to write this anymore. We can write this. So how do I write this in this specific case?
Don't you have to have a 1 over n?
Oh, so you're looking at the right, the top left.
Oh.
No worries. 2 points for Matthew. So this would become x of 2 plus 1. Did that make sense, Matthew?
Yeah.
2 plus 1 plus c. So f of x is simply 3x cubed divided by 3 plus a constant. So f of x is equal to x cubed plus a constant. Questions? We basically made a complete circle. We started with the function f. We applied the derivative operator to both sides to create a function called f prime. We then apply the antiderivative operator to both sides of this new thing called f prime. And we go through the steps. We end up right back where we began with f. Please. So whenever you find an antiderivative, you end up with this extra possibility, 2 points for Gabe, that maybe it's really plus 10. Because if you start with this, Gabe, right here, you start with a formula 3x squared, and you're working backwards. You're trying to find the antiderivative. Like, where did this come from? Well, 2 points for Gabe. We'll go to Ella. Ella, what's the derivative of this right here? If I apply d dx to both sides, this side's going to become f prime. Ella, what will this become on the right? Nice. 3x squared plus 0. That's the whole point. 2 points for Ella. That if I start with this, and I'm trying to say, where did that come from? Well, it could have been x cubed plus 10. It could have also been x cubed plus 3. It could have been x cubed minus 20. It could have been x cubed plus 0. We just don't know. And so we have to account for the possibility that if I'm starting here and trying to go backwards, yeah, there might have been a constant with the formula that I started with. That makes sense. Good work. Please.
So do you ever have to find the constant, or just leave it as is?
So there are 3 cases we'll deal with. If they tell us to start with f prime, and they want us to go find the formula for f, like we did, they might also say, oh, and by the way, the value of f, we'll have Blake help me here in a second, the value of f when x is equal to 2 just happens to be 11. So once I get this formula, I can use this information now. So Blake, how would I combine this formula where I don't know the value of c, that's what Lucas is asking about too for Lucas, with this information? Can you see how to put those two together?
Well, to find the constant, okay, since you're putting f as 2, you would replace the x with 11, right?
Oh, close, just the other way around.
Oh.
So the way I remember it is this. Here's the x inside the parentheses. Here's a 2 inside the parentheses.
Oh.
Therefore, the 2 is the x.
Okay, so 2.
So what would I write?
Oh, f of 2
There we go.
equals 2 cubed plus c.
Yep, because we don't know that value yet. 2 points for Blake. I need to write a little bit more there. What else would I write, Michelle?
Like equal to 11.
There we go. And then how would that be useful, Michelle?
Then you can find the, or you find what the constant is.
Yeah, nicely done. Because 2 cubed will be what, Michelle? Pressure. 8. No worries. It's just when somebody's asking you, your brain freezes up. So what's the value of c, Michelle? 3. So yeah, there will be instances where they'll expect you to find the value of c, like that. Not really a big deal. Some instances, they don't expect you to find c. Like if you look at problem 3 in this packet, you'll notice that for problem 3, every answer ends with plus c. Jake, please.
So if you go back,
Yeah. One more. Come on board. That one.
yeah. So if you take the derivative of f like you did of x cubed, and then you find f prime, and then you take the antiderivative and you get x squared plus c, can you just keep repeating that and you'll get like an infinite amount of c's, constants?
Oh, gotcha. So I started with this formula here. I find an antiderivative, which is this formula here. Without this extra information, we have no clue as to the value of c. It's just some unknown number. Could be 0. We take the derivative of this yellow. That gives me back to this formula here. Because the derivative of c would be 0. And we're right back where we started.
Oh yeah.
So that's a perfect circle. Like it won't change. It'll just take the antiderivative, we're right back to the yellow. Does that make sense?
Yeah.
Is that your question?
Yep.
It's good work. 3 points, please. Go
I
ahead,
have a
Sam.
question about the blue sheet.
Yeah, please.
So it says n cannot equal 1 or -1. Is that only for the expanded power rule and the power rule? Or does it go universally across the entire rule?
So only for the power rule and the expanded power rule. Yep, good question.
So basically, with these rules, we're making a big circle.
We are.
Okay.
Yeah, and it's actually the first time we've been able to do it all year, where we can say, hey, if we start with a formula and we apply the derivative operator, the green rule sheet, we create a new formula. We now have the capability of applying the antiderivative rules to our new formula, which we called f prime, and we end up right back where we started with a formula for f, except for the little glitch of the constant. 2 points.
But what are we gonna use this for?
So here's how we use it. Multiple uses, but for today, here's how we use it. We go back here, and we say, I don't have a calculator, so I cannot compute the integral as shown here. Like, I can't do this integral because I don't have a calculator, available to me. So come on, board. So the fundamental theorem says, since I can't use my calculator, I'm going to do something else. I'm going to find the antiderivative of this green formula. I'm going to find the antiderivative of this green. And instead of doing a million computations, once I have the antiderivative, I just do 2 computations. And I get the same answer. Like they're the exact same thing. The fundamental theorem says those are the same thing. That makes sense. 2 more. Anybody else? Okay, so can I erase what's on the board here? So kind of a fresh start here on your paper. We know that this formula, whatever you want to call it, doesn't really matter what we call it. The fundamental theorem says if we go find the antiderivative of that formula, we can compute the value of the integral in a different way. So I look at my blue sheet, and I look at this formula here, and I have to find a perfect match. And I find it using the expanded power rule. So we'll go to Tara. So if I'm trying to make this right here in green, oops, look exactly like what I see, come on. So right here in green, look exactly like this. I have to be able to choose an A, a B, and an N. So what's A, Tara? B is also, and N is? Perfect. So, it says here 2 for Tara. Says that if I'm trying to find the antiderivative of something of that form, I can just write down the answer like this. So actually, let's write this on your paper. Write antiderivative. If you don't put numbers, it means antiderivative. It doesn't mean integral. Kennedy, please.
So when it says 0 to 3 on the integral, that's just
The 0 and the 3 are indicating that this is indeed an integral. And if I could use a calculator, I would. I would just pick it up, type it in, be done. So that's the objective.
But for calculating the antiderivative, use those.
Right. So what we're doing is, like, we're kind of putting it all together. We're saying we want to compute the integral. We can't. So this equal sign says we can do something different. We can instead focus on what's happening over here. So we're focusing on the orange in order to accomplish the blue. Like, we want to accomplish this blue task over here. We want to accomplish this. We can't, so we're going to do the orange instead. First step is we must find the antiderivative of this little piece here. So that's what we're going to write down. We need the antiderivative, no limits, of x plus 1 to the 1/2. That's what we need to find. 2 for Kennedy. Before we can do anything else, we must find that antiderivative. So we'll go to Chris. So Chris, is it legal to say that this yellow box here is an exact copy, like no difference whatsoever with this orange box here, as long as we pick A, B, and N correctly. Are they exact matches?
Yes.
They are. As long as A has what value?
1.
B is,
1.
and N is.
1.
That means, 2 for Chris, we'll go to Kaylee. That means we can write, instead of this orange box, we can replace this yellow box, because orange and yellow are identical. So orange and yellow are the same. So we can replace the yellow with this green box over here. So what do I write right here, Kaylee, next to this equal sign?
Number one's just 1.
Keep going.
And then it would be x plus 1
I'm just put a 1 for emphasis, but keep going.
plus 1 to the power of 1 half plus 1 over 1 half plus 1 plus c.
2 points. Questions? Okay, so we got to get you to say it now, so we'll go to HT. So HT, I got all these different formulas on the board. I'm going to start circling some of them. Let's circle this one here. How is this green formula related to this yellow formula?
They're equal.
So this part is equal, 2 points for HT. This entire box, so this yellow box, there's too many colors. The yellow box is equal to the yellow blob. But what we're looking for is, we'll try, let's go to Elena. Yellow box is definitely equal to yellow blob. That's what the equal sign is telling us. We got to remember what green formula inside of yellow box. It's really interesting. Delana, how is green formula now circled in orange? How is green formula related to yellow formula, Delana? There we go. The green is the derivative of the yellow. So said the other way, the yellow is the antiderivative of the green. That's how they relate. So let's clean up the yellow blob there for a minute. So this is just 3/2 power. This is dividing by 3/2. Dividing by 3/2 is the same thing as multiplying by 2/3. So we would have 2 multiplied by 1x plus 1 to the 3/2 power. The whole thing would be divided by 3 plus a constant. Question? Go to Natalie. Natalie, how is, and don't let this fool you, it's not meant to be a trick, I just want to make sure you're following. Natalie, how is black blob, black formula, related to yellow formula?
It's just the same.
Yeah, those are the same thing. Black and yellow are the same, we just wrote it a little different. That's why it says trick question. Natalie, how is black formula here? How is this black formula related to the green formula over here?
It's the antiderivative of the green.
Nice. So black is the antiderivative of the green. Therefore, green is the derivative of the black. 3 points. Question? Please, Matthew.
For 1 plus, half plus 1, where did that go?
What I did is this denominator would be what fraction, Matthew?
3/2.
Good. Dividing by a fraction of 3/2 is no different than multiplying by a fraction of 2/3.
So it's just the reciprocal.
Just reciprocal multiplication. 2 points. Anybody else? Solid. So we can test this by doing the following. We can take this formula in black and we can find the derivative of that formula. So we're going to do that over here. So we're going to have d over dx of 2 over 3, that's just a multiplying constant, times x plus 1 to the 3/2 plus a constant. We're going to find that derivative. So make sure everybody's following still. So go to Peyton. So when I use my green rule sheet, Peyton, to find the derivative of this stuff in parentheses, what am I expecting to find? I am. Do you know exactly what equation I'm expecting to find? We've got lots of equations on the board. We've got this equation in green. We've got this equation in yellow. We've got an equation in black. We took the black equation and we rewrote it here. We're going to take the derivative of that equation, 2 points for Peyton. We are going to find the green because that's the complete circle. We started with green. We found the antiderivative of the green. That gave us the black. Therefore, the derivative of the black must be the green. Question. Cool. Let's go to Ella. So Ella, we've got 2/3 is a multiplying constant. We just pull it out. So now we must take the derivative of this. How do I write the derivative of that, Ella?
3/2 the power of x plus 1.
So what's the new exponent?
It's just 1/2.
There we go. Because you take 3/2, subtract 1. Then you multiply by d over dx of the x plus 1. And then we have plus c. What's the derivative of the c, Ella? Nicely done. 2 points for Ella. And Ella, what's this going to equal?
Just 0 again?
No, because you'd have dx dx, which is
What?
plus d of 1 over dx, which would be, so 1 plus 0 is, good. So this is 1. 2 more for Ella. So now we have, what do these two multiply to become, Ella?
Sorry, I can't see.
Oh, my bad.
Just 1.
Those are also 1. So we're left with what we expected. X plus 1 to the 1/2 power. We completed the circle successfully. We're right back where we started. This formula here in brown is exactly the same thing as the green formula. That's what we mean by antiderivative. Please, oh, go ahead, Tara.
So how do you get the answer?
Getting close, we're getting close. So, the fundamental theorem says we have our antiderivative. It is the black formula right here. This is our antiderivative of the green. So the fundamental theorem says if you can't integrate the green, which we cannot, instead we can evaluate the black, is how I'll say it. Because all we have to do is plug into this black formula 2 numbers, 0 and 3. So now let's show how to write it. Can I erase this? Okay, let's make a copy actually in case we need to go back to it. That's 7. Now we're page 8. Okay, cool. Clear that. So now write a new thing on your paper. I did tell you this was somewhat involved initially until you get good at it. Even then it can be involved. So rewrite the problem, 0 to 3, x plus 1 to the 1/2 dx equals. Okay, we are trying to integrate this formula that I keep circling in green. Because we can't, the fundamental theorem says go find a different formula. So we did. We'll put our new formula in black, just like it was on the other page. our new formula, the antiderivative of the green, is this black, 2/3. So I'm going to write 2 over 3 x plus 1 to the 3/2 power plus a constant. I'm supposed to take that new formula. So look up here in the fundamental theorem again. Here's the green. Here's my black formula right here. I'm supposed to plug into that formula 3 and 0. So there's some new notation. Here's the new notation. Put an equal sign there. You draw a bar, you write 0 and 3. That means exactly the same thing as that. It means take this formula right here, take this formula, and plug into that formula a value of 3 for x and a value of 0 for x. Just like the fundamental theorem specifies. Questions? So we keep writing. So we go to MJ now. So I write equals. I'm supposed to take this yellow formula, MJ. I'm supposed to plug into that formula a value of 3. So how do I write that, MJ? You do. Yeah, the C is just a number. We don't know what number it is, so we just write down that number. 2 points for MJ. It's really good. And then we've got to take all of that minus. Now, because we're subtracting, we've got to be careful. Let's put a parenthesis just to make sure we don't make a mistake with not subtracting everything that follows the minus. And we'll go to Chris. What would be the next thing we write?
Minus f of 3.
So what we did f of b. That's this piece right here. Now we've got our minus. We've got to go f of a. So how do I write that out? So remember, we were integrating the green formula. Integrating the green. The fundamental theorem says, instead of integrating the green, go find a different formula. Go find the yellow formula. And then put into the yellow formula this number and this number. So we have put into the yellow formula a value of 3. We now must put into the yellow formula a value of 0. So what would I write?
2/3, and then in parentheses next to it, 0 plus 1. To the power of 0.
No, 3/2. Does that make sense? 2 points for Chris. Questions? Please.
Actually, I'll ask him.
Very good. Anybody else? Awesome. Let's go to Kennedy. It's common for people to forget what 3/2 power means, so let's talk about it. With 3/2 power, Kennedy, you can either, so this number inside the parentheses, Kennedy, is what number? 4. So we have 4 raised to the 3/2. That means we can either take 4 cubed, or we can take 4 to the 1/2 power. 1/2 power means square root. So Kennedy, which appears easier? 4 cubed or 4 to the 1/2 power? Correct. 4 to the 1/2 power is equal to what, Kennedy? 2. So now we had 4 to the 3/2 power. We have taken care of the 1/2 portion. So now we have 2 cubed. So 2 cubed is 8. So 2 cubed is 8. So what we have now is we have 2/3 multiplied by 8. 2 points for Kennedy, plus a constant. Does anyone need me to go through that again? Jake, go ahead.
I still got it, but I just did, since if you take 4 to the second power, it'd be 16. And if you took 4 to the 1, it would be 4. So I just put like 4 times the half of 4.
Well, that's interesting. I've never thought of doing that. So what you did is this. You said I've got 4 to the 3/2 power, right?
Yeah.
You said I'm going to first do 4 squared. You're still going to have to do a cube somewhere. That's interesting. You did this. And then you're going to take all of that and cube it?
No, I just did, so I just kind of broke it apart. So I did 4 to the 1 power, and that left 4 to the 1/2, and 4 to 1/2. I just took half of 4. Maybe it's just a coincidence. But
Like
yeah,
that?
that's what I did.
Is that what you did?
Yeah.
And you got 4 to the 1/2 is,
2.
and then 4 times, so that gave you 8, right?
Yeah.
Hold on. I think it's actually right. It just takes me a minute to remember, because I've never done it that way. No, that's true. That's actually true. That's very good. I'll give you a ticket for that. That works just fine. Please.
Yeah, logically that makes sense to me with the orange that you doesn't for some reason.
That's interesting. I've never thought of doing it that way. I don't know why. That's really good. Okay, remember, don't do any homework at home. I'm going to finish this and if anybody's interested.
So I was wrong. Max didn't even show up. He slept in 2 hours. And so it's just
My dad's playing in the MX Pro.
I bet he forgot.
That's short. Yeah, it's the second year playing that Pro. Just culture things.
Does Matt just skip this period? Does Matt just like skip this period? 700 every once in a while. He just decides, I don't really feel like going to one of my hardest classes. 14:30.
You're welcome. What's that? You know you don't not at all. We just kept guessing and eventually it came out right.
Like, so if you take this other formula, I found the 5.
No.
So why did we go in the circle? Was that just to explain?
So it was important to understand what antiderivative means.
Okay.
The reason we had to understand what antiderivative means is the fundamental theorem is all about that. The fundamental theorem says if you're trying to integrate this green
Yeah, that doesn't
thing
work for everything.
and you can't, then an alternative is to go find the antiderivative of the green. That's the yellow. Once you have the yellow, all you have to do is plug in the 2 numbers. So that's what we did over here. We said, okay, we're trying to find the integral of this green. We can't. So instead, we found the antiderivative of the green, which is the yellow. And we plugged into that yellow formula the 2x values. And we subtracted. And that is the exact same thing as doing it. That's what the fundamental theorem is telling us. That's why we had to do the circle to get understand what that meant. Oh no, I went in a circle because all of our brains will remember something better if the brain can complete the connection. when your brain has this hanging connection, it struggles to remember. But doing this has value because you're like, okay, at least I saw it once. I think my brain can make the connection that if I start with the green, right here, and then I go find the antiderivative of the green, I'm going to get this black formula. If I take the derivative of that black formula, hey, I'm right back with the green. That's the circle. I don't need to do the circle on this problem. The only purpose of doing the circle would be to kind of check my work. Does that make sense?
Can I try
Oh,
something?
please. Let's stop the video real quick.